All right, we're live. We did it. We did it. We did it. Let me send this to in the chat. Here is that. Beautiful. Let me go to the book. Let me send it in another chat. So that way, because I have someone that's not in this Discord anymore that actually wants to be a part of this. You can all hear me, right? Like anyone, let me know if you can't hear me.
Yeah, you're good.
Okay, cool. Probably sound like crap. Sorry. But I'm on Wi-Fi, really old laptop, AirPods. I'm on like a very I'm not on my normal setup.
Excuses.
Yeah.
We expect perfect audio from you, Matt, at all times.
I'm sorry, it's my fault. All right, this one should be pretty quick. I don't want to like take up too much time today, partially because I'm all the way in California. Uh, so been a little busy today. Just came back from a conference. I have to fly out tomorrow, and life. So for those that don't know, this is a book club. We're reading Designing Distributed Systems, this book right here. Unfortunately, like if I page fit this, it's gonna be tiny, but I will for a second. We're reading Designing Distributed Systems. It's a book that kind of covers patterns of how you can design these distributed systems, right? Like different patterns. It gives you patterns that you can use when you're working on and creating distributed systems. Again, it's only like 150 pages, this book, and it doesn't go into super like depth on the topics. It just kind of introduces you to the patterns. So we're on, I think this is meeting 5, assuming that my numbers were correct, and we'll be covering chapters, I believe it's 7 and 8, if I'm not mistaken. Yep, 7 and 8. So we're going to be covering scatter gather and functions and event driven processing. Cool. So scatter gather, and let me page with this one. Um, Last week we spoke about the sharding and we also spoke about replicated services, right? So the author kind of goes into the chapter on scatter gather and saying, hey, we've discussed how to scale systems in terms of like requests per second, which is using the stateless replication pattern. And we also discussed how to scale systems based on the size of their data, which is using the sharded patterns. And in this chapter, the author is introducing what's called the scatter gather pattern, which uses a form of replication to scale up, like in terms of time, right? So scatter gather is essentially as it sounds. You scatter out all your requests across n number of nodes, and then once those n number of requests return back to you, you gather it all back up and you return that back to the caller. And again, sorry for my resolution. I'm on this really tiny laptop. It's actually really tiny, so sorry.
Do you want me to? Oh, never mind. It's on YouTube.
Yeah.
I was gonna ask if
I'm
you wanted
sharing
me
in
to
Discord,
stream
right?
it, but that's all right.
Did I share in Discord already?
No.
Oh, I should do that. Let me do that real quick. Share screen, entire screen. Oh, this might not work actually. You probably are going to see black. I'm pretty sure you all are going to see black. All right. I won't share the content because I don't think I can. Unless I'd probably have to share in Discord first and then start OBS up. Not really worth. Okay, we'll just talk about it. But pick up your copy of the book. I mean, here, I'll put the book in Discord real quick. Voice 3. Here, that's the book. Uh, Nothing in the book is like super. Like, I'm not really going to refer to so much in the book that we can't talk about over voice. The some of the documentation or the diagrams are actually pretty cool to look at, but they're kind of simple. So if you just pull them up in your book on your side, you'll be fine. Or if you want to just look on the YouTube side, you'll see it there too. But yeah, so scatter gather, right? So author says we learn how to scale up requests per second. We learn how to scale up when our data is really large. How do we scale up when we want time sensitive things to happen? And he gives us this diagram in the book where you have a user that makes a request to your system. Your system then scatters those requests across n number of backend nodes. Those backend nodes return to you, and then your service then gathers all the results back up together, and it sends the result back to the user. So this is the whole idea of what scatter gather is, and basically what the author puts in the book, and he says it allows you to solve like a parallel problem. So in this case, each backend node, so like the author says there's two different kind of like forms here. Each backend node that you want to scatter to can be a homogeneous node where it knows how to respond to every request, right? And respond to all data for that request. But generally speaking, when you're doing the scatter gather approach, you're breaking up your request such that your each backend node can respond to just a subset of the data. So it sounds similar to like sharded services in that sense, but it'll make sense once we get into like more of the examples here. Basically, you take a problem and you cut it up into n slices, and that's what you scatter across. And the author gives an example here and says, hey, imagine you have you need a service request, and it takes you 60 seconds for one CPU core to answer that request. Well, if you can parallelize that and you have a 30 core machine, well, now you can take it. Each core can now take 2 seconds to process, or sorry, the entire request can be processed in 2 seconds because you've taken that request, split it up across 30 cores, and since each core can operate on 1 minute, now you do 1 minute divided by 30, and it's 2 seconds per core, per node. So the grand total of time is now 2 seconds to handle that request rather than 60 seconds, right? 60 seconds per one core or 2 seconds across 30 cores. So you can see how using parallel execution techniques via this scatter gather pattern can help you lower the time it takes for you to respond to requests. And I think the author gives a nice graphic on it when we talk about a different example. But any questions so far? I'm not really reading Discord chat because I only have one screen right now and it's hard to like balance them. But if you have a question, just like interrupt and I'll be happy to chat with you about it. But any questions so far? Maybe I'll pull up Discord on my phone so I can see life.
Not really a question, but like, well, I guess a bit of a question. So this is essentially the same pattern you'd see in programming when you're basically writing like a multi-threaded or even like multi-process application in some cases, right? Where it's like, oh, if you have, like in the simplest case, it's like, okay, if you have more cores and you can split the program into separate threads, right? It's like the same idea of splitting it up and then gathering the results into like your main process. It's
Yeah,
the same idea just applied
same idea.
to distributed systems, right? So I guess my main question is, this pattern would only like, you would only really want to apply it in the case that your data is too large or like the processing is like insufficient on like one machine, I guess. Is that sort of
Uh,
its application most of the time? Because otherwise I feel like it would be better to just keep it like programmatically like on the same machine instead of like splitting it
yeah,
into all these
it's
other virtual machines.
both, right? It would be
Mhm.
both essentially, not necessarily both exclusively, but one or the other or both is why you would want to use scatter gather, right? If you are trying to scale up requests per second, we already saw that we can use load balancers to route your requests across n number of nodes, and you're kind of in a weird way using a little bit of scatter gather there, where like you are scattering the requests across nodes, but you're not gathering them back, right? You're not scattering one request across n nodes. You're just giving a random node a request, right? And then in the sharded system, you have a large amount of data that you can't fit on one box, one machine. So you shard that data up, and then requests go to that shard to be serviced. In the scatter gather approach, you're taking that one request and you're kind of slicing that, and then you're setting that request to multiple nodes so that you can decrease the time it takes you to service that request. And generally, this is important when you have a request that like just asks for a bunch of work to be done, and you can actually logically cut that request up into smaller sub requests. For example, if,
Mhm.
if all of us in this chat right now, if I asked you like, hey, I would like you to get a list of all pizza places in your town, or sorry, if I asked all of us to like get a list of pizza places in the United States or something, right? I know it's a really large ask, but if I asked you to get a list of pizza places, That's a request. That's one request that I'm asking you to do, the system to do work on. I can scatter gather that request by saying, hey, you get all of the requests for pizza places that begin with A, or you get all requests for pizza places in New Jersey. I get all pizza places in California. Somebody else gets all pizza places in Texas, and we do that again and again, and we split that out,
Hmm.
and then all of us are now doing a subset of the initial work, but we all have to return before the initial request can be fulfilled to the caller, right? And that's the gather side. So as you give me back the pizza places in New Jersey, and I give me back the pizza places in California, and somebody else gives me back the pizza places in Texas, I can gather all them together and be like, hey, user, here are all the pizza places in the United States. Does that make sense?
Yeah, I mean, I was just saying, like, I guess in this case, it's sort of like at a higher level. So it's like you said, you can have both where it's like, okay, you're parallelizing like the actual like functions for whatever, like you're making a request to some API and it does stuff and it can be parallelized, but it could also be parallelized like at the request level from like basically a layer above like your application where it's actually solving that problem.
Yeah, exactly. And again, this is just a pattern. So like if you see like
Yeah.
you can apply this pattern at your application level or something even before your application. This is just that pattern. But the idea is that you take one request, you scatter it out, they do the work, and then you gather all the results back, and then you respond to the request. So that's kind of the high level
Right.
idea.
I guess, okay, sorry, follow up then. So I guess is this pattern like in the in the context of like distributed systems, is it more likely to be applied to like actual requests, like handling requests, like whether it's a web request or whatever, as opposed to like where is this, because the splitting of the work has to happen somewhere, like you're saying you have to make like sub requests.
Yep.
That happens like at the client level, I guess. So like the client does some work and it's like, okay, I'm going to split up all of these into different requests, and then it can hit your like endpoint or your API that has all of this, not sharding, scatter gathering, I
Yeah.
guess,
It depends on how the
and it can handle
application.
that.
Yeah, it depends on how the application is presented to the user or the client. Generally
Hmm.
speaking, the client is not going to be the one responsible for the scatter gather part of it. It would be your application, right? So, like in the example that I gave, if the
So
client's
it
asking me,
accepts a single big request, then it's like, okay, I'm
right,
going to scatter all this,
right, right,
and
right,
it'll
right.
handle it on the back end.
Yep,
Yeah.
exactly. That's
Okay.
exactly. That's the like the general like traditional use case, right? You could have a smart client that could know to do that itself, but generally speaking, you're going to be the one doing it, right? Your application.
Okay.
Cool. And then the
Cool.
author gives like a little hands-on distributed document search where he says, "Hey, I'd like you to find all documents that contain the words cat and the words dog." Right? So when you think about that problem, you need to find all documents that have the word cat. You need to find all documents that have the word dog, and then you need to find the intersection of the documents that have both of them. Right? So this is kind of like an intersection problem, right? You can gather this. And I'm just going to go to the diagram because I think this explains it perfectly well. If I asked your application, I said, hey, application, give me all documents that have cat and dog as words inside the document. Well, your application now can perform scatter gather to find that information out, right? Because it can scatter based on the words that you're looking for. So it'll go to your backend application, say, hey, find me all documents with cat. Hey, find me all documents with dog. It can run those in parallel. I mean, it doesn't have to be strictly in parallel, but it will run them concurrently. And as those results come back, your root node, your application would be like, hey, thank you for all the documents with cat. Thank you for all the documents with dog. Now I'm going to like kind of dedupe them and find all the, the intersections there and send that back to the user. So in this case, given the example in the book, documents 1, 2, and 4 have the word cat in it. Documents 1, 3, and 4 have the word dog in it. The intersection between those documents is just 1 and 4, right? Because those are the ones that are the same between both cat and dog. So that would be the gather portion. That's what's going to get returned to the caller. Any questions on that side?
Sorry, one more.
Yeah, that's fine.
So I thought I may have read it wrong, but I thought in the case of like the scatter gather pattern, you weren't usually like duplicating all your data. Because in this example, it seems like, well, each leaf node has to have like the full set of data. If it's going to do like one search for cat, it has to look through all the documents.
Yep.
And and for dog, it has to look through all the documents. So does that mean it has like two copies of the data, or are they just
Correct.
both referencing like the same point in data and they just like have their own references, or do they need to actually copy that? Because I thought that was one of the benefits is like you don't want to have to copy all the data across the whole thing, or is it just depend on like the problem you're solving?
It depends on the problem you're solving and how you want to set it up. In this example, yes, both nodes are homogeneous, meaning they can service any request. They're not sharded. They have all the data they need for every request that can possibly be given to them. We're just happen
Okay,
to,
but that
yeah, sorry, go for it.
I was gonna say yes, but that could work like if like your problem here is like okay, well you need to make searches and you want to join them, you need to have the whole data set.
Yep. And that's where we're actually heading to. So the author says, okay, this is great, but this actually requires that all nodes be homogeneous and they have the ability to handle all user requests. You can also use scatter gather with sharding, where the leafs or the things that you're scattering requests to are sharded, right? So that's what he says here in this paragraph. I don't know if you have the book out. I mean, I know like on YouTube, but in the thing that I highlighted, it says, but at a certain data size, it's necessary to introduce sharding in order to build a system that can hold more data that can be served on a single instance. So yes, in the previous example, we're assuming that every backend leaf that gets that gets scattered to is homogeneous and can serve all requests. Now the author says, hey, we don't have to just do it that way. We can also shard the backend leaves, and our scatters can go across those shards. And that's what we'll see next. So the author expands the example and he says, "Hey, forget about the cat and dog stuff. Let's let's look across a large document set, right? Maybe all patents in the entire world, and you want to find, you want to search on those patents. Well, you can shard those patents from like, patent 0 to 1 million, or sorry, patent 0 to 100,000 are on this node, patents 100,001 to 200,000 are on this node, and so on and so forth. And now you've sharded your backend nodes. Now, when you do a scatter gather, you're still gonna scatter across all of your backend nodes, but each backend node only knows about a subset of the data. So if you make a request to the system, you say, hey, give me all patents that have the word rocket in it. Now you'll scatter to all of your backend nodes. Each backend node will only know about a subset of the patents, and it'll perform its work and then send that back to the root node. The root node will gather that up and send it back to the client. And I don't know if he put a figure. Yeah, here's a figure down here, 7.3. So this is now another step forward where each backend leaf node has a subset of the data. It's sharded. So any questions here so far? And he illustrates the same cat and dog example here in the diagram where he says, hey, search for every document that has cat and dog, but now each leaf node, instead of having every single document ever, it only has a certain subset of documents. It's sharded. Now, if you're thinking about this and you're like, okay, I get why I would do this. This makes sense because now if I have an extremely large data set, I can split them into my backend nodes across these different shards. But you might be, thinking about this now. What happens if one of those backend nodes doesn't return or it fails? You lose a subset of your data, right? Like you can't fully satisfy the request because imagine if like this middle node fails and it doesn't return you that document 15. Well, now the thing that you're going to return to the client is going to be incorrect because it's going to be missing document 15. And the author basically in the next part of this chapter says you can combine the best of both worlds where you have this scatter gather approach with the backend leafs using sharded data, but the backend leafs are replicated, right? And that's kind of like where he goes. And you can see how this whole book is kind of like layering these patterns on top of one another to like counteract some of the trade-offs that you have to accept when you choose a pattern. Sorry, I know there's a little lot. So any questions there so far?
Nope.
Cool. Yeah, if anything, just interrupt me. And then the author says, listen, you need to choose the right number of backend leaves. He calls the backend nodes that you scatter to leaves. You need to choose the right number of them because theoretically, if you can have an unlimited number of leaves, it'd be great, right? You can parallelize across all of those leaves and everything will be super fast. But that's obviously impossible to do. So you have to choose the right number of leaves that you need for your work. Um, and if you choose too few leaves and too many leaves, you have different problems, like depending on what you do. And the author shows some pretty cool math here. So he says, like, imagine if you had like a service that has a 99th percentile of 2 seconds. That means that out of 100 requests, essentially, right, 99 of them return in under 2 seconds, but that one request takes longer than 2 seconds, right? So 1% chance that a request will take 2 seconds or longer, right? And that sounds good. That's like a 99% like performance. Everything is returned under 2 seconds, 99% of the time. But that 1% of the time that it returns longer than 2 seconds can be a problem when you have a scatter gather system. So let's see. So you might be saying to yourself, okay, I have a system, it can return under 2 seconds 99% of the time, over 2 seconds 1% of the time. Now I scatter gather that out. So I introduce 5 leaf nodes, right? Now you've just taken your 1% chance of a request taking longer than 2 seconds, you've increased that now to 5%. Because each node has a 99% chance of being under 2 seconds or a 1% chance of being over 2 seconds. So if you do like 99 times 99 times 99 times 99 times 99, you'll get 95%. So you can see how this is called the straggler problem, meaning you now have 5 leaf nodes that have the 1% chance of taking longer than 2 seconds. And since you have 5 nodes this time, through the magic of math, you multiply their chance out, and now you have a 95% chance of being under 2 seconds, or now a 5% chance of being over 2 seconds. And that becomes a problem because in the scatter gather pattern, you need to wait for all of your backend leaves to return or to be finished working before you can send the response back to your client, your user. So what the author's trying to say, the point the author's trying to make here is choosing a very large number of backend leaf nodes is going to it's going to basically scale up your performance issues and make them more apparent, right? And if you did the math for 100 leaves, right? If you take 99 and if you do 99 to the 100, you'll basically be guaranteed that your request will be longer than 2 seconds. Any questions on this? I know this actually took a minute for me to wrap my head around at first, but it makes sense once you sit down and like read it and you're like, oh, okay, I get it. So any questions there? I think I did the math on my phone too. I went like 99, like to the 100th essentially.
Yeah, because it's what
1% decrease every time you multiply it.
Oh.
Or not decrease.
Yep.
But
yeah, I know what you're
pretty
saying.
much.
Yeah, so if you do like 99, if you do 0.99, to the 100th, you'll get 0.36 or 36%. So now you've just taken your service and said, from 99% of the time you'll return under 2 seconds. Now you've just dropped that to 36% of the time you'll return in under 2 seconds. Or if you flip it, 64% of the time you'll return over 2 seconds. So like adding more of those leaf nodes actually introduces these performance problems at a higher frequency. So be careful. What the author's saying here is be careful. Choose the right number of leaf nodes that's acceptable for your SLAs and monitor your performance and adjust as necessary. That's all the author is really saying here. And he's just showing us the math so we can understand like why that works. Cool. And the author makes like 3 little conclusions here. And he says, listen, increased parallelism doesn't always speed things up because the act of processing a request on each node has a little bit of overhead, right? You have to make an HTTP request, wait for an HTTP response. That takes up a little overhead on your CPU and your network. Increased parallelism doesn't always speed things up because of the straggler problem, which we just saw with the math, right? If you have a 1% chance of things taking a long time, you now increase that chance as you add more nodes. And then he says the performance of the 99th percentile is more important because each user request actually becomes numerous requests to your service. So any questions on like this straggler problem or the math behind it? I'm just looking ahead real quick. Cool. And then the author ends the chapter with what I've already kind of covered before. And he says, listen, having homogeneous leaf nodes sounds good on paper, but now you have to replicate the data across them. Okay, so we sharded our leaf nodes. Okay, but when you shard your leaf nodes, you have the possibility that you have the straggler problem. So what do? You make the best of both worlds, and you combine both approaches, and you have leaf nodes that are replicated and sharded. So now you counteract the straggler problem because you have a higher chance of being in that 99th percentile of performance, and you don't have to replicate all of the data across all of your leaf nodes. And that's how the author kind of ends this chapter. And that's scatter gather, right? It's if you're coming from programming, you might have heard this kind of like a fan out, fan in pattern. And if you're actually looking online about like resources about this and you want to read up more, you can look up terms like scatter gather, or you can look up terms like fan out, fan in. And like fan out, fan in, if you ever seen one of those like those handheld fans that like generally like women used to have them, right? Where they like open the fan with their thumb, right? And it's like it fans out like a peacock like feathers, and then it fans in. That's kind of the idea, right? You fan out to multiple backends, and then you fan in as you collect them. So scatter, gather, fan out, fan in. Those are some of the terms you can look up if you want to read up more about this stuff. Awesome. Any questions before we jump into chapter 8? No, Matt, we love you. You're best. Yeah. No, I'm just messing. I feel so weird not having like my dual screens right now because I can't monitor any of the chat or anything. I feel slow. I feel slow.
Don't worry, nothing's happening in chat.
Okay. Good. Cool. So we'll move into chapter 8. So chapter 8 talks about functions and event-driven processing, and the author goes into this chapter saying, hey, so far we've examined design patterns for systems that have long-running like services, right? You start your service and it runs until you kill it, right? Or until it dies. And that's great, right? Because if your service is always up and running, then you can send it requests all day and it's going to respond as soon as it gets it. And that's a great pattern if your application has a sustained load, right? So for example, Google.com, it's always under load, right? People are always using it. It's always under a pretty good load. It makes sense to run the infrastructure for Google.com as a long-running service. But something like a notification service, maybe like a email subscription service, you might not want to keep that running 24/7 because you don't really get email subscribers coming into your system day in, day out, right? Like there's some of those websites have those little forms at the bottom saying, hey, subscribe to my email list. You don't want to keep the service that's running that up 24/7 to respond to an email subscription because you're not constantly getting hammered with email subscriptions. You might get one a day, you might get one a week, you might get one a month, whatever. So in that case, you might want to move that sort of service to a more event-driven design. And what we mean by that is you send events to these systems, and then your system responds to that event in many different ways. One of the popular ways to have an event-driven architecture or an event-driven system is using what we call functions as a service, or FaaS. If you've used AWS Lambda before, that's a function as a service. There's other tools as well out there that have their own. And basically, it's just a piece of code that's sitting there. And when it gets a trigger, it runs. It runs the code. So that code is not always sitting there running, waiting. It's the code is there, not running, not executing. But when a trigger event happens, and that can be like an HTTP request, it can be like some sort of other trigger that you have, a webhook, whatever. When that trigger happens, the code essentially wakes up and executes that request. So it's more of like an on-demand or event-driven. So this is a really, really cool architecture, but it has some pros and cons. The author makes a really good note here to disambiguate what he means by serverless computing and functions as a service. Because a lot of people see like functions as a service and they say, oh yeah, you're doing serverless. Not necessarily, right? So the author makes a really good point here to say like serverless, like the idea of serverless computing can apply to a wide variety of computing services, but it depends on like if you're running the servers or not, right? People tend to think of serverless being like function as a service things, but it's not just limited to function as a service. You can have like a container orchestration service, like a managed Docker, managed Kubernetes, and that would be serverless because you're not responsible for managing the servers. But you can also have an open source functions as a service system running on your own machines, and that's not serverless, that's event driven. So he just basically gives you a little aside here and says, hey, don't assume that functions as a service and serverless are the same thing, because they're not. And Neon put in the chat, like, serverless seems more like a business term. Right, exactly. That's pretty much what it is. If your business or your teams don't have to operate the servers, we generally call that serverless. But since most of the serverless tools out there happen to be functions as a service tools, people confuse them, people confuse function as a service with serverless, but that's not the case. And the author just makes sure to point that out because it's true. So just keep that in mind when you're talking about this stuff.
Actually,
So,
a question
yeah, go for it.
on the serverless topic. So like you would also consider like you might refer to like serverless infrastructure or something if you have stuff hosted on like something like Google Cloud or AWS, right? Would you call that serverless because you're not running the servers? Because I feel like I've heard it mixed in with that like
In that
concept as
case,
well.
like,
Or is it more specifically like you're running code on a server that's not yours?
yeah, so if you are going into like Amazon right now, AWS or Google Cloud, and you're spinning up a virtual machine and you're managing that virtual machine, that's not serverless because you're the one still
Okay, because you're still
responsible.
managing it.
Yeah, like you're still responsible for that
Okay.
VM and whatnot. But if you go into those same cloud providers and you say, hey, give me Postgres, right? Like, give me your Postgres database, and you didn't spin up a VM and whatnot, that's more of a managed service. And it's more like serverless in that regard, because
Okay.
you're
So
not the one
it's
managing the servers.
okay. So even if you're doing like a platform as a service like thing where it's like they just give you whatever and you just give them the code and they host it and do all of that, you might call that serverless as well.
Right. Yeah, exactly.
Okay.
And I think you hit it. I think you hit it spot on the head. It's kind of like a little businessy buzzword term, right? Like,
Yeah.
yeah, as long as you understand what it means, you're good, right? But don't sit here and be like, we have a serverless platform running in our data center. No, you don't. You're running it in your data center. You are managing the servers. You may be providing a serverless platform to your like developers from their perspective, but you're still managing the servers. It's not serverless. Like, it's one of those weird
Yeah,
things.
it depends on your
Yeah,
perspective and all
exactly.
that. Yeah.
Exactly.
Okay, cool.
So yeah, so functions as a service became really popular in the last like half a decade. Lambda from AWS is probably one of the most popular ones. There are other ones out there too, but I don't remember all of their names. I think OpenFaaS is one that you could run yourself, but I haven't played with it. Anyway, functions as a service, it enables developers to get their code from their machines to running in production like very quickly. Because think about it, right? You write some code, you compile a binary, you upload that binary somewhere, and then you have to deploy that binary somewhere. That's a lot of steps in there. A lot of developers don't really even know what those steps do or what those steps are. So serverless allowed you to just write code on your laptop and then just send it to Amazon or send it to whatever your function as a service provider is. And it just took your code and it was responsible for running it. So it really like lowered the barrier from coding to production. And that's why it was such a popular thing. But functions as a service are really good for this event-driven computing like pattern, but they have their pros and cons. the author goes into the benefits and he says, listen, the benefits, let's not joke, like let's not like fool ourselves. The benefits of function as a service are primarily for the development team, right? It simplifies the act of getting your code running. It simplifies the fact that you don't have to manage your code or scale it up or down or whatever. And like it's just very granular and allows you as a developing team to focus just on developing, right? So if you think about this, the benefits of functions as a service are primarily focused on the developer team, right? The only real benefit here that the user sees is the scale automatically like benefits, right? So this whole function as a service like product field is really targeted at making developers' lives easier, not necessarily making the customers of your applications' lives easier. That just happens because your developers can spend more time now. So those are the benefits, right? And again, if you like function as a service and you're like you love it, that's great. But there are some drawbacks that you should be aware of if you're going to use it. So let's talk about some of those challenges. Um, when you use a function as a service like tool, or you're running, function as a service, you can't have like local memory essentially, like local state. You have to pull whatever state that your applications need to use from some sort of like storage service, right? Now, each of your functions are decoupled from one another. So if you have a function that reads in an HTTP request and then like responds, you can't actually like store that in memory. You have to kind of read that from a place and then respond to it. Similarly, if you have a function that reads like some sort of user data or some sort of data for your application and then responds to it or mutates it, it can't just store that data in like local memory. It has to read that data from some sort of storage device, do some operations on it, and then store it back somewhere else. And you can imagine that process when you chain functions together, you can't just pass the output of one function as input to the other function. You have to kind of store it somewhere, and then the next function can read it from that place you stored it, and so on and so forth. All right, so that's one challenge. Any questions on that so far?
I have one.
Yep.
So when he says you can't read stuff into memory, is that more like, okay, you can't access disk, like you don't have access to files or anything, but you can still like obviously read stuff into memory because you're making like requests to an API or to a database or something, so you can actually operate it in your like on that data in your function. So it's like you're accessing memory because you have to store all that somewhere.
Right, yeah.
But it just
Exactly.
means you can't like write to disk or whatever, right?
Exactly.
Or
you can't write to disk, or you can't have a global variable across two functions, so to speak, right? Where
okay, yeah,
you know what I mean? That's kind of the memory.
Yeah, that was
he's
my
talking
next
about there.
question.
Yeah.
Like if you configured two functions, they would have to be like two components in this like function as a service, right? You couldn't like
Exactly.
contain them both within one.
Exactly. They're each function in this function as a service like model, they're entirely independent. So whatever you do in one function, the other function will not see that. So if you need the other function to see that, you better store it somewhere else, right? Store it in some storage server. Yeah. Again, this
Okay, cool.
I think this book was written in maybe I don't remember when this was published. But either way, it was in development for a while before it was published anyway. These functions as a service providers are getting better, right? Does things now, you might be like, well, Matt, there's a functions provider that does this, and that. Like, yeah, they're getting better every day, right? But the idea is that each function is completely independent, and if you want them to communicate, you have to like store the output of the function in one place and then have the input read it from that place. Cool. And then another difficulty. Oh shit! I think
did your mic switch to your phone or something?
I think my AirPods just died hard.
Oh, okay.
Oh,
yeah, I think it switched mics on you.
Yeah, is it better now?
Yeah.
Yeah, I think
it was coming from your AirPods or something.
Yeah, I have to Oh, I don't think they died. I think I just killed Bluetooth. Did I do that? Oh, my Bluetooth driver probably just shit the bed. You see this? Look. Alright, anyway.
Oh no.
Yeah, I'll keep it on this. I think, let me see if OBS is still recording. Yeah.
I hate when that happens on Linux.
Is the mic like unbearable, or should I lower the input?
It's good now. It's switched back somehow.
No, I just lowered this little input in the top right. because I have to keep
Okay.
that high for AirPods but low for internal mic.
Yeah. I think it's fine now. It sounded like it switched and then was like echoey and then it
Yeah.
switched back.
Yeah, sorry about that. Yeah, that was weird. Anyway, I think my Bluetooth driver just died on this computer. Anyway. Yeah, so another like weird thing about functions as a service is that you don't have a really comprehensive view of your service. Right? Like when you program, you write functions that call other functions and you have an idea of like how those functions are chained together. And when you do function as a service, you don't really know like how your functions are being called and what order and what like you don't know anything. And it would be possible to create a loop where you have like function A calling function B calling function C, and then function C calling back to function A, and then looping forever. How do you detect that loop in function as a service? Because from the function as a service provider's perspective, it'll be happy to keep executing all your functions and charging you money. How do you find this, right? So the observability and the ability to see what's happening is kind of limited in the function as a service model. So you're going to need to adopt really good monitoring in order to like see what's going on. Questions there? Did I switch back to Bluetooth by any chance? I don't know.
Nah, I think
now
you're
I'm
good.
afraid of my system.
I'll let you know. Don't worry.
Okay, yeah, let me know. Cool. So function as a service is really good for those like ad hoc event-driven systems that need to like wake up as requests come in, right? A request comes in, wake up, do the work, spin back down. It can save you money. But as requests, like as you increase the number of requests coming into your system and you have a sustained number of requests over time, it might make sense to switch off of function as a service and to go somewhere else. And the author talks about this need for background processing. There are going to be some workloads that you have in your application that require some sort of long-running background process in order to do the right thing, right? Like long-running computational things, transcoding video, compressing log files, whatever. But there's going to be some work in your system that is a long-running background process. And those types of work are really poor fits for function as a service. They should go to a different type of architecture rather than function as a service. And if you think about it, the whole idea of functions as a service is you pay per request to your service, whereas some of these background jobs you'll pay per like the data used or the consumption, right? So you have to keep that in mind when you're choosing to use functions as a service or not. So just keep that in mind. That's another trade-off. And then there might be some things in your application where you need to hold data in memory, right? So maybe you need to pull a bunch of user data into memory so you can operate on it, or you need to consult your database to get an index of things and operate on it. If you use a function as a service model, a request comes into your application that triggers the function as a service to become alive and start executing. Now that function as a service needs to load all this data from from storage into memory, operate on that data, and then return the result to the user. That's a long time. That's a pretty high latency if you think about it. Now your function as a service, since it has to load all that data into memory on every request, you have a super high latency interacting with your users. So that's another thing to think about if you're trying to use the function as a service model. And then the author goes into the cost of having request-based processing. Paying per request sounds good when you have a low number of requests, but once your requests scale up and you start to get sustained levels of requests, paying per request kind of sucks, and it might have been more cost-effective to have long-running services. So what the author's trying to say here is there might be a point in time where maybe you start on function as a service, but then you migrate to long-running services later to reduce your cost. So just keep all of those in mind, because those are some of the trade-offs you need to accept if you're going to use function as a service. Any questions so far?
Nah, you good?
Cool. All right, and then the author starts to talk about some of the patterns for function as a service,
And I think he talks about what, 2 patterns or 3 patterns? I don't remember. Let me consult the side. Yeah, just a few patterns. He says one of the first patterns that you can probably use with function as a service is called the decorator pattern. And the decorator pattern is basically just a fancy way of saying, like, I'm going to do some mutation to my data before I call another function, right? That's literally all that's happening. You can kind of think of it almost as like a middleware in a weird way. And that's kind of the context that the author uses in this particular example. He says, hey, imagine you had some sort of API that takes JSON, and then some of the fields of the JSON need to like default to certain values. But you know, when you omit a value in JSON, it defaults to null, right? So you can put some sort of function as a service decorator in front of your HTTP API that receives the JSON, does the mutation on it to default some variables that weren't provided, and then pass it to your actual function as a service handler or your backend service, right? So now you've decorated your request there using a function as a service like decorator. And this is pretty cool because imagine trying to do that in your code, right? Imagine if you had some lines in your code that says like if field equals null, set field to true. If you put that in your application code, now that particular code has to scale up as your application scales up. Whereas if you use this decorator pattern, you can scale the decorator independently of the app code, right? So you get some interesting benefits if you split this out or not. And this is just one pattern that the author gives you, is the decorator pattern. And that's pretty much all he says about it. Any questions on that so far? And I think the code actually makes sense if you want to read it on the screen. It's on page 86 if you're following the book. Cool. All right, and then the author starts talking about event-driven systems. So we talked about functions as a service. We know that functions as a service is like a way to like, write functions and give them to some sort of function as a service provider, and those functions will get executed once some trigger happens, once some event happens. And the author starts to talk about handling events, right? So generally speaking, you have a system that is request-driven, right? A request is made to your system and it does some work. Another request is made, it does some other work, another request, so on and so forth. And then you have other systems that are more event-driven, right? Like a user signed in, a user subscribed to your email. Those are more events rather than requests. So the author differentiates a request-driven system from an event-driven system by saying a request-driven system is kind of like think about a session, right? A session is just a user trying to use your application, and as a part of that session, they make requests to do different things. Whereas events are more of like a single instance thing that happens in your application, and it's generally meant to be processed asynchronously, right? So that's kind of how he defines it. It's not like perfect in stone, but if you think about that, it makes sense on like digesting the rest of this paragraph. So think of events as like things like, oh, I've signed up or I've signed into your service. I'm triggering a welcome email, right? Or I need to send notification to an email subscriber, right? Those are kind of events. And the author even says like a machine that's about to reboot, that would be an event, right? Because that would trigger something. These event-based components are a really, really good thing to use in like a function as a service model, right? Think of the whole idea of like two-factor authentication, which is what the author kind of goes into. He says users are going to sign into your application and they're probably going to have two-factor authentication enabled. If you need to do a two-factor authentication like token send, right, like send the actual token to someone's phone or their email, should that be a long-running process? No. Should that be like something that's like request-based? Not really. It should be event-based, right? Whereas this event happened and it queues up this job to be done and it gets done. So the author talks about that and he says like, here's how it would look in practice, and this is how you can provide low latency, because now since this is event driven, as the events come in, these pieces of code are executed rather than waiting for, the ability for a request to be handled. And he gives us some code here. I don't know if I find the code super helpful here, but he gives us some kind of pseudocode to see how this would work in practice. Any questions on this though?
That might be legit Python.
No, I mean it is legit Python. I'm just saying
What is? Okay, it is.
Yeah,
Okay.
yeah. It's we don't have access to the other code.
Yeah, there's some modules he's probably using the Twilio and stuff. I guess I did have a question. So, it seems like it would be silly to use this pattern for a lot of things. Like it would get complicated pretty quickly to add this code in sort of a separate way to your application, right? Because it's all this code, it's not going to be stored with your main source code, is it? Because it's going to be on some platform like Amazon or whatever, where it runs these functions as a service as decorators or something, right?
Exactly. It'll be deployed adjacent to your application. Right. And your application will know to trigger the event, but that's it.
Right. I think it does mention in there it gets really complicated to troubleshoot some of that stuff.
Yeah. It does.
It just makes me wonder what are there must be some specific use cases where it's particularly useful because you don't want to build it into your app for whatever reason, but it's the cost of not being able to troubleshoot the problem easily is there's a trade-off there, so it's it must be worth it for some cases. I just don't know. I can't think of any.
Yeah, it's really good. When you have things that are event driven and they can be done asynchronously, you might not want to put that logic in your application, because now that you're putting it in your application, if your application's overloaded, how is it going to be able to process that well? And especially in the case of the two-factor authentication, right? This is a really good example because you log into you log in to a server, right, or to a service. You put your username, you put your password, you hit enter, and then it prompts you for your two-factor auth token, right? Could you imagine if the application needed to send that two-factor authentication token, if your application needed to be the one to send that out synchronously, and then your front-end JavaScript could not move forward to the next screen until the text message was sent? That'll be a bad user experience, because we know how long it takes to get text messages. It can be instant, or it can be in 30 seconds, right?
Well, yeah, but obviously you wouldn't have to do it synchronously.
Right.
All the time. There are methods to do asynchronous stuff.
Yep. Or even if you don't want to do it synchronously or whatnot from the client side, even if your server had to deal with it, if your server is busy responding to a bunch of other requests and it's overloaded, and now it has to send out this two-factor auth token, not really a good pattern, right? It would be better off to separate that out into another function or into another area and call that with some sort of event trigger, And that's kind of what the author is saying here. That way, that code is it can be scaled separately from your application. It doesn't have to put burden on your application, and since it's not super time sensitive, it gets handled, but the user doesn't see the delay, right? Because it's on a part of the code that's okay to have some delay on. And same thing with
right.
You ever go to a service and it's download your log file, and your log file will be available for downloading. We'll let you know when your log file is available for downloading, right? That's a perfect use case for event-driven architecture, right? When you click that download button, an event fires and says, hey, get Neon's data, right? And then later on, once that data is ready, another event fires and says, Neon's data is ready, notify them, right? That's a perfect case for event-driven. You don't need that code in your direct application. Those are going to be done via these event-driven architectures.
So,
like for your app, is it usually just you trigger it with like an API call or something, and it like triggers the event essentially, or is there
Yep,
like
pretty
some
much.
other mechanism?
It can be like a webhook, callbacks, things of that
Yeah.
nature, right?
Okay. Okay.
Cool. And then the author, I think the last thing is like, so instead of just handling events, you can have like a pipeline, and we kind of actually just talked about it with the whole download thing that we just talked about. But instead of handling like a single event, you can have like a pipeline of events. Whereas like something happens, it triggers some function or some code to run, that finishes, that sends another event, that triggers more code to run, that finishes, it triggers more code, and so on and so forth. And you could think of that as like a pipeline of connected different events and patterns. Right? So that's what the author's talking about here. And the author says, what's the difference between having this sort of like event pipeline that we're talking about here and a traditional like microservices architecture? And the author says there's two differences there. One, the first difference is that like long-running microservices are great, but event-based pipelines are really good when the nature of your data is event-driven, right? So like if you have a more event-driven pipeline, you might want to use, if you have a more event-driven like system, you might want to use like an event-based pipeline rather than long-running microservices, right? Also, these event-driven pipelines are generally very asynchronous, so they can connect various different asynchronous things together. Whereas like these long-running microservices, why would you want to have these long-running microservices taking up your CPU time if they're only called like on demand, right, every now and then? A quick example the author gives here is saying, imagine a human like approving a Jira ticket. If that was a microservice, that whatever listens for the approval has to always be running to listen for approvals in a microservice architecture. Instead, if you use an event-driven pipeline, well, the approval action will trigger that event, and then things will run. So the author's basically saying here, like, think about the trade-offs here when you're choosing like a microservice architecture versus like more of an event-driven architecture. And of course, like everything in technology, you can mix and match them, right? You can have certain things doing a microservice architecture and other things more event-based. Cool, and that's pretty much it. The last example is just pretty quick of, I don't think the last example is like the best. It's just basically saying like, here's how you can do a pipeline where the user logs in and required actions run and then optional actions run, and he's just basically showing like a pipeline here, right? Like login triggers required actions and then it triggers optional actions, right? That's like a pipeline. I didn't think this example was that great, but whatever. And yeah, and that's it for this chapter. Any questions on functions as a service, event-driven architectures, so on and so forth?
Not really a question, but I see this. Am I getting an echo?
Maybe. Let me lower my volume.
I see the event-driven stuff a lot in IoT applications. Like, for example, if you are monitoring vibrations of an engine or something like that.
Yeah.
And then something changes, then it fires an event, and then something else happens. So people use Lambda a lot for that.
You use what for that? Sorry.
AWS Lambda functions.
Yeah, that sounds great, right? Because they would essentially listen for triggers, and that would be more of
Yes,
an event-based.
For IoT devices?
Like monitoring stuff, like safety or...
Yeah, well, I'm thinking you probably wouldn't, because if it's like an IoT or embedded device, you would obviously have like a lower level events, essentially, where it's like, okay, well, if there's like a safety concern, it's like, oh, it shuts off the engine, but that's not something that's going to be hitting a Lambda function. Like maybe that happens later if it needs to like record it or send a SMS message to people. It's like, oh,
Yes,
hey,
exactly.
this thing shut down. But that's like something higher. Like it's like the operation does its thing, and then it's like, okay, now that I'm done with that, maybe it does something like that. I don't know enough about IoT to say, but it seems like it would be like a secondary concern most of the time.
Yeah, I think both are valid. I was approaching it in the sense of like you have some sort of Ring doorbell camera, and the doorbell is pressed. There will be a instant event happening locally to ring your actual doorbell in your house, but then that would also fire an event to like notify you via your mobile app, right?
Right.
And that happens over the internet. But I agree with you. IoT devices are a little weird because the very nature of embedded systems are that there's some sort of like real-time operating system running on it, so they can do things very quickly. But these more modern IoT devices that have internet connectivity do send events out to be processed later. Right.
Yeah, that makes sense.
Like motion event, like I'm talking about cameras now, but like motion events when your doorbell's rung, blah blah blah.
Yeah. Yeah, there are lots of things. Like if you have a Raspberry Pi, you can just have pretty much lots of monitoring.
Exactly. And yeah, a Lambda function in AWS would be a great recipient of those events, right?
Yeah. Then you can fire out whatever need to be done, like different things.
Exactly.
Notifications and stuff.
Yeah, it would definitely depend on like your use case and like it's like safety concerns or like just however it's being used. If it's just like a camera, then yeah, it probably makes sense to just embed it in the thing, right?
Exactly.
To be able to do that.
Yeah, or like for example, monitoring systems like intruder.
Yep.
Like, yeah.
Exactly, and that shows, I think, a really good example of these architectures, right? Like, you are going to mix and match. There are going to be certain things that you want to process right then and there that are built into the application code, and there are going to be things that can have a little bit of delay, and you can just send an event for them. And this is a really good example of using the different patterns together to get like the benefits that you need, you know? And if you haven't played around with like functions as a service, I really encourage you to go spin up a small one and like put a little HTTP trigger in front of it where you send like a GET request or whatever and make that your trigger and just watch it do its thing. You know, it's really cool to see that and see how it responds to the events and whatnot.
Yeah.
I have played with it a little bit. Like you can have an S3 bucket and put something in there, and that triggers.
Yep.
Lambda function. So.
One of my Discord bots is running in a function as a service provider, and when I do.
See, I've been thinking recently about like where like what would you like? It would be weird to host like a Discord bot like on like a server, right? It makes a lot of sense that
it's not weird. I mean, it's just it would have to always be running. Yeah, it's overkill. Unless it's a very active Discord bot, then yeah, you might want to serve it. But mine, you know, it's just a simple little bot where you type in like /LeetCode and it gives you a random LeetCode question. And when you do /LeetCode, it sends the request to my function as a service. It wakes up my bot and the bot responds. But there have been times where I've noticed that my bot would take too long to start up because maybe it hasn't been run in a while and my function as a service provider like deprioritized it, and then I run the LeetCode thing and it's like, hey, this failed because your bot didn't respond in time. And then I run it immediately afterwards and it works because my function is now loaded and hot cached, right? Like it's there. So it's like, but that's some of the disadvantages of function as a service, right? Like since you're on demand, you can be too late, you know? So, but yeah, I really encourage you all to play with it and spin some up of your own. And
I assume, are there like different APIs for like different languages and stuff? I guess like can you run like a Lambda function in Python and Go and JavaScript? Or whatever, or
so
is it like its own thing?
Whatever provider you use, they have different runtimes that you can use, and they usually support all the major languages, right? Like Go, Node, Python, Java, right? They usually support all the major languages.
All right.
The Discord one is running in Go, so that one's supported. Yeah. And for the scatter gather stuff, like if you want to play around with that, you know, look up terms like scatter gather or fan in, fan out, right? Or fan out, fan in, whatever. If you're in JavaScript, though, you might not be able to really take full advantage of that kind of pattern, just because of JavaScript's more single-threaded, event loop nature. But you can kind of see
Yeah.
what it is. If you ever use JavaScript promises, there's like promises or promise.all or promise.any. Those are kind of that like scatter gather approach almost, right? So like take a look at those APIs and see what it gives you. But yeah, any last minute questions?
What are we next 2 chapters next week?
Yeah, so next week is going to be kind of cool. We're going to cover ownership election, where you can have multiple nodes like agree on the idea of ownership and who should like handle requests and blah blah blah. Really cool stuff because a lot of applications out there use this concept of ownership and elections and whatnot to do their work. HashiCorp Vault is a really good example. They use an ownership process to handle that. But then we're also going to like go into part 3 as well, and we're going to talk about work queues. So we're going to kind of span across part 2 and part 3, and I didn't really want to do that, but I do want to finish the book on time, so we'll do it anyway. So yeah,
Okay, cool.
9 and 10 next week. Bring your questions, and thanks for all hanging out.
Thank you so much.
You're very
Good to
welcome.
see you, Matt and Remy.
All right, I will see you all next Thursday. Bye everyone. I'm gonna end the recording.
Adios.
Oh no, not exit. Just stop.